Hello. Hope am I audible to all of you? Wait for few minutes, or else we'll start our session. So before starting session, does anyone have any doubt regarding the course that we are learning, the essentials of oxidation, reduction, and carbon-carbon bond formation, and its application in organic synthesis? So uh, we have completed the week 4 of this course, and today we are here to solve any problem that or discuss the problem that if anyone have in the course, the content from this week 4 course. So before going to start, I will introduce myself. Hi, I'm Vijay Ran. I'm a Prime Minister Research Fellow in the IIT Delhi and also in the University of Queensland. So, so before going to the slides that I have added here to discuss, so if anyone have any doubt, so that we can discuss right now. So if none of have any doubt, then we will directly move to the slides, right? So here we have seen the Fleming oxidation, and this is the reaction, and that I have mentioned here, the Fleming Kumada oxidation. So it is a stereoselective oxidation of alkyl silane into the corresponding uh, alcohols uh, using per acids. So let's say we have the starting. In this case, the the starting that I have mentioned here. I'll just enlarge the structure so as it is good for you to understand. So we have such secondary starting material, and the reactant in this case is the HF or HBr or HI. So it will be HX, and we have the per acid, that's the AR C double bond O, OH, and the base, and followed by the next step will be the hydrolysis step. So in this case, what happens? The HX, so the proton from the HX will be here. It will be a ipso substitution reaction followed by the X minus. In this case, let's say fluoride. This fluoride attacks on the Si, and it gives the intermediate, and which intermediate get when the per acids, the hydroxy group, the active one. So in this case, among these two hydroxy, the hydroxy which is I have highlighted here in the terminal hydroxy is more active because the lone pair on this hydroxy group is involved in the conjugation with the carbonyl group. So this lone pair attacks on the silicon and followed by the removal of the X minus. So it's like kind of the beta carbocation, and which is stabilized by the silicon group. So that's the uh, intermediate happens here. So if you look at the detailed mechanism for this one, is the intermediate that we have seen here. So if this intermediate is in the next step is formed like in this manner, the Si OO, and this peroxide linkage with the group. So this is the intermediate, and which is then uh, so the it's kind of a rearrangement in at the center. So we get intermediate in this fashion, which has the OSI bond. So initially we have the carbon silicon bond followed by the peroxy linkage. Uh, so after this rearrangement, and so this entire R group is migrated to the oxygen. This group get removed from this the starting, and again the second molecule of the peroxide attack on the silicon. So So we get the another intermediate which also have the peroxy linkage, and it's occur three times. So again we can see here the third time it's occur. So entirely all silicon have the SiO bonds, and this later in the case after successive attack again by the ORL group as like the earlier attack. So we get the star intermediate and followed by the hydrolysis of this intermediate gives the gives us the alcohol as a product. So there are many several times the peroxy group attack followed by the attack of the anion form in the steps. So the anion. So let's say in this case you can see this anion, that is the AR C double bond O negative. It attacks on the silicon. So we add the excess of peracids as well as the in situ form anion helps to final cleavage of this sorry, the attack on the silicon, and followed by hydrolysis. On hydrolysis we get the enolate, and which on protonation gives us alcohol. So that's like several steps involved in this reaction. But a similar, but the utility of this reaction, if you look at um, the start, the steps involved, the HF stands for HF, followed by the peracid, and then hydrolysis. We get from the alkyl silane to alcohols. So this is a- this reaction useful for the formation of the alcohols. If you look at the some more examples in this case, so here in this case we have the another type of reaction, so which involve the instead of per acid we have the peroxide, which is H2O2, right? Here the linkage is the similar linkage is as like the per acid. So this linkage is common in this case, and this is the modification. So a previous reaction that we have seen, which was the Fleming-Kumada oxidation reaction, which involve the starting. You can see here the HX plus peracids, sorry, peroxides, peracid, and followed by the hydrolysis. And in this the modification Fleming-Kumada oxidation, we use the uh, oxidation. This is the oxidation of alkyl fluorosilane. So in this case, so the R Si. So here there are two fluoride groups in the R, though alkyl fluorosilane to their corresponding alcohol. So we get the alcohols, and so alcohol here, the since R is there are two R's, so we have added the two equivalents of alcohol we get. So this is the variant of the Fleming-Kumada oxidation. So the mechanism you can see here, we have the fluoride in the starting. Here we are using the KF salt. In the initial case, it was HF, and also instead of peracid in the initial case there was AR C double bond OH, right? That is the peracid. So this is somewhat of some kind of modified Fleming-Kumada oxidation reaction, and in this case we are using the AF, that is the salt. So the F minus attack on the silicon, it forms the intermediate in this fashion, and this intermediate, which has the pentavalent intermediate with the negative charge, this get attacked by the peroxide, that H2O2. So it forms the intermediate, the second intermediate, and again in the similar fashion, there will be a rearrangement of the R group from the RSI bond get cleaves, and it forms the RO bond. So we get the uh, the linkage like ether linkage ROSI bond, and the similar manner second peroxide attacks, and again we get the another ether linkage. So this one first and the second, so the two OR linkage from the one starting material, and upon hydrolysis it gives the two alcohols, right? So two equivalent of alcohols we get. So this are may be similar or different, but at the end we get the from each R group R Si bond get cleaves, it forms ROH bond. So this reaction is good for your solving assignment question. There are some examples which have the synthetic utility of these both the reactions, and the similar examples I have mentioned here. So here in this case we have the starting, which has uh, the Si Me2 functional group, and which on reaction with the sodium bicarbonate followed by the peracids. So it gives the alcohol, right? So this entire group converted into the OH group. Further, another example is with this is the Fleming, right? And this is the Fleming Kumada, and this is the uh, Timao Kumada oxidation, right? Here you can see we have such intermediate, sorry, the starting, which has the SiO linkage with the ethyl group. And if you use the peroxide, the H2O2, Kf, and KHCO3 in the THF solvent, we get the cleavage of this bond. So we get the alcohol group as well as OSI. This later convert into the, as we seen, as we add the excess of peracid, so H2O2 in excess. So excess peracid, earlier seen similar kind of rearrangement, sorry, oxidation reaction occurs, and we get this another group also convert into the corresponding alcohols. And in this case, the retention in the stereochemistry occurs. That also one of the key point that you need to uh, keep in mind. So these are in this both the two oxidation, the retention in compression occurs in both. Also, the silicon based starting materials were used. We convert which convert into the alcohols that you need to keep in uh, note. Further reaction. This is the one of the question that you can uh, uh, take as it is from the lead from this the slide to solve one of the question. I will just show the question probably. Yeah. So Anna, yeah, this is the question given. So if you look at the question, so what's happening in this question, or the similar intermediate given, and it is like acetone in presence of HClO4. So what happens when you add the acetone in presence of HClO4? So I will just insert a new slide. So let's say we have any hydroxy group, 1,2 hydroxy, and let's say the stereochemistry also, if I mention, so to mention stereochemistry better, I will like add it in the ring form, so it will be easy for understanding. So we have the such substrate, and we have the OH hydroxy group. This hydroxy, again another hydroxy group. The third hydroxy group is also downward directed. And if you use the acetone, I will just write the structure of the acetone. So if you have the acetone as a reagent and HClO4 in terms of HClO4, so what happens? The protection of 1,2-diol, 1,2-diol occurs, and the condition is this 1,2-diol should be seen to each other. So in this case, so there are the one, it is A, B, and C. So if you look at the stereochemistry of these diols, so the B and C, they are seen to each other, right? So that's why what happens. So the protection of these diols occur. So if on in terms of this reaction condition, so group the OH which is anti, which is not getting protected. So this is what happens in this case. So let's say when we have any group like OH here, at that time also, the protection doesn't occur. This protection doesn't occurs, but this occurs because these both two are seen to each other, right? So the protection with the acetone, it occurs on the scene protection of this 1,2-diol should be in same plane, right? So if it is with both hydroxyl is in same plane, then the protection occurs. So the next step is the first step. So if you look at this, if you look at the this reaction in the stepwise, I will just remove this slide. If you look at the stepwise, so what happens in terms of acetone? So this OH hydroxy and this hydroxy get protected. If you look at the other remaining hydroxy, they are not 1, 2, 1, 2, 3, 4. So they are the 1, 3. So the protection doesn't occur, but this protection. So the first step will be in this manner. So in which the hydroxy here, the hydroxy which is beta, both this one. So the hydroxy groups get protected, and this hydroxy group remain intact as it is, and remaining groups also will be when same, and followed by the PCC oxidation. What do the PCC do? PCC do the oxidation of alcohols to keto, right? So the oxidation of alcohols to keto occurs. So in this case, so this alcohol get converted into the its keto. And also, I just forgot here. So if you look at the stereochemistry of this hydroxy group and this OH, they are also get protected. So this also get protected because acetone, obviously it will be acetone is a solvent in this case. So acetone already there is in excess. So if you look at the stereochemistry, they are also seen to each other. So yes, this is also 1, 2, not 1, 4, 1, 3. So this hydroxy group also get protected, and the first step is this one. The second step is with the PCC. So the PCC with the PCC, the protection, sorry, the oxidation of these hydroxy groups occurs. So this is the product in this reaction. So you can easily select the which is the correct product among this. The next question, before going to the this slide, I will just put the in between one question. So uh, the another question is based on the this is somewhat this is also one of the question. And if we look at the question, the concept behind this question, solving the question. So what mentioned the major product formed in the following reaction, and here we have given the CN. So it's like a C triple bond N, and we have given the LDA, which is the base, and this molybdenum complex. So we'll see the structure of this molybdenum complex. This reagent is for the alpha hydroxylation of the enolates. So if you have the oxodiperoxy molybdenum pyridine hexamethyl phosphoric triamide. So it is the this this is the molybdenum complex, and this entire name of this complex, which is the name of this complex, and the short form for this complex will be the MOOPH. So this is the complex, and this is the achiral complex, because if you look at this one, so it has the plane of symmetry, right? So it will be obviously the achiral complex, and it react with the uh, we have the starting which has a ketone, and especially in terms of such ketones. So when this LDA react with the LDA and this molybdenum complex react with this one, it forms uh, chelate in the fashion. Uh, so the LDA abstract the alpha proton. There will be two protons here, right? So one and two. So the alpha proton, once it abstract the proton, it forms a enolate, and this enolate, when it react, enolate will be get stabilized by the lithium. So if you just let's say there is another R group, and when we add the LDA, so it forms generally, preferably it forms. So here there will be, let's say, just for simplicity, there are tertiary. So obviously it will form preferentially the inlet in this O negative, and this O negative is generally. So this is the enolate. In the similar manner, here also the enolate gets formed. But let's say once the enolate is formed, it gets chelated with the lithium, and since we are adding the this molybdenum complex, it forms a six-membered cyclic uh, structure. So when the another uh, hydrolysis of this occurs, so the pro alcohol in this case, we get alcohol which will be alpha, that is directing downward, and again this keto enolate, since this enolate got back and followed by the we get the exo product in this case. So ratio also given exo to indo 5:1. So basically we get the chiral product. Although we have started the reagent with a chiral, but intermediate that we get here in this case is the chiral. Sorry, the product we get here is the chiral product. So this occurs in case of the when we use the ketone, but when you use the cyano compound, in that case, what happens? In the similar reagent, LDA with the molybdenum catalyst, molybdenum OPH, we get the enolate followed by the uh, alcohol formation, which will be the exo one. So this is the two difference. So in this, when you use the ketone, at that time we get the endo as the major product, and when we use the cyano group instead of this keto, at that time we get here the alcohol, which is a exo one, right? So these are the two key differences. So you can easily select the correct answer among this one. So obviously when you use the cyano compound and we are using the LDA as well as the molybdenum as a reagent, so we get hydroxy group, which is a exo. So you can select the correct answer from this one. So this was the another question that I have selected, I have taken from the assignment. So without instead of directly taking the question we will see some concept before, and then we'll move to the which is the correct answer for this one. So here I mentioned we have learned the regarding the oxyridine, and these oxyridine compound are useful for the many functional group conversion. So if you look at the oxyridine, so it is useful for alpha hydroxylation. So in this case, oxygen as an electrophilic oxygen. So we can use that the oxygen. Same for the epoxidation of the alkene to epoxide. Also the uh, sulfide to sulfoxide formation. So we can use that uh, oxaziridine as a reagent. Also, we can use for the aziridine formation. So from alkene to aziridine formation. So in this case, nitrogen used as a electrophile. So it is a quite good reagent. So it can donate the electrophilic oxygen in the reaction, this first, second, and third. And also for the uh, electrophilic nitrogen can also use for the formation of RNase to the hydrogen, amine to the hydrogen. Also aziridine formation, sorry, aziridine formation from the alkene to aziridine formation. Also for alpha amination reaction of the ketone to alpha amino ketone. So in the last three cases, this aziridine oxaziridine based complex or based reagent used for as a used as a nucleophilic nitrogen of from this one, and also we can use the electrophilic oxygen to form the epoxide as well as the alpha hydroxy ketone, also for the sulfoxide formation from the sulfide. So this is the synthetic utility of this one. We see some rearrangement reaction also, which is based on, we have also seen the rearrangement reaction of the, especially the Barton oxidation. So this is just the mechanism for this one. So it will be useful. It's just a revision for you to get back to the get to the answer from one of the question. So if you look at the Barton reaction, so use the ONO, which is the as a functional group here, and there will be a there should be one, two, three, four, and five. So this there should be a hydrogen to get so this type of the compound get converted into the alcohol. So in place of this entire, so when we put kept the reaction mixture in the light, it forms a uh, OA, this radical, the bond cleavage of the homolytic. So if I just draw the, so this is how the homolytic cleavage of this ON bond occurs in terms of light, and it forms the O radical. This O radical get interact with the uh, uh, proton present on the alpha, beta, gamma, let's say gamma position. So this hydrogen and this oxygen radical forms a partial bond followed by the OH bond formation, and the radical will be transferred to the radical is transferred to the carbon, and this NO radical then get get forms a bond with this one. So we get the hydroxy group formation from the unfunctionalized CH group. So if you have some unfunctionalized CH group and we want to make the activate that one, so it's kind of CH activation. So abstraction of proton from the sigma carbon occurs and followed by the radical formation of the carbon. So in this case, radical formation of the carbon and then the NO bond formation, right? So, and this NO we can further modified into another functional group. But main thing is we can able to activate the CH bond using this Barton type of oxidation reaction, and this is photochemical transformation. And in this case, the member transition state occurs, which is favored. So if you have some starting which have the let's say the bridge, let's directly take the example. Yeah, here if you have the some bridge such uh, structure, and if you look at the alpha, beta, and the gamma, so at this point there is no any hydrogen. If you move to this one, so here there is one hydrogen. Then beta, alpha, beta, gamma, there is hydrogen. So this here there are three hydrogen present. This is although it is symmetric. No, this is not symmetric because it is the so this CH3 and the CH3 which is written in the blue, they are not symmetric in this case, right? So, so there are three possibilities. Also, alpha, beta, gamma. So obviously this is it is also the same. So there are and also there are two hydrogens. So in this case, so there are four possibilities occur. So with this reaction, so H nu and then followed by the uh, this is the reagent which is from the Wittig, right? So what happens in this case? The first step will be the formation of this ONO get converted into the OH. But which OH? So in this case, the five-member ring, sorry, the six-member transition state should be the preferable. So you have to look at the which bond gives the five-member transition state and which is among this one. So at that position, the OH bond gets formed and followed by, I'll just let this mechanism, right? This ONO bond formation occurs at this position. So you have to identify which CH2, sorry, which hydrogen in this all the four possibility is favored and gives the reaction at the center. So you can, if you look at that one, then definitely it's easy question. So I'll just show the what are the options that we have here. So right, so this is the question, and we have given the H nu and the I2. I2 as a catalytic generally used, not catalytic in this case. So first step will be the OH bond formation, right? Then this Barton oxidation occurs. Preferably, it occurs at the CH2, this one. So at this position, the Barton, just select the so this will be the first step. So in which the methyl group, which is the on the same side with the ONO bond, it will be get activated by using this only by using the light. So that was uh, the first step in this one. And if you look at the second step, I will just I show the correct answer for this one. I'll just stop here. Yeah, right. First step is that is the formation of OH bond, and in presence of I2, that's the some critical part in this one. So I'm not sure which is the correct option here, because if you look at the next step, which is the Wittig salt, the complete set of reagent is not given. So I'm not sure in this case. So what should be the correct option here? Because only the Wittig salt, where is the no base is given, because to activate this further, once this hydroxy, so it will be EN4, right? And this will be the hydroxy group in this case. And once this form, Further, the next step should be the formation of iodide. Just so preferably, uh, but again there is a reagent with the Wittig salt. So I'm not sure which is the correct option here. We'll wait for the answer key for this question. So moving to the next concept of the LiHMDS. So this LiHMDS is a base, and if we directly move instead of moving to this question, so what does this base do? In this case, the base abstract the proton. It forms the enolate, the same case, and as we seen earlier, the use of the oxyridine. So this oxyridine, uh, as we see, this is the oxyridine reagent, and how it can act? It can act as a nitrogen, also act as a nucleophile, sorry, electrophile, or oxygen can also act as the electrophile. So in this case, the oxyridine given, right? So in this case, what happens? Once this proton is abstracted, the nitrogen from this one, uh, so in this case, nitrogen as well as the uh, oxygen both can act, right? So among this one, so in this case, the hydroxylation occurs with the oxygen act as an electrophile here. So and also the stereochemistry in this case is important because this methyl group is beta. So the stereochemistry of the bond will goes to the alpha in this case. So this alpha bond will act as a alpha hydroxy group we get as a in excess, and this is the utility of this that the reagent that we seen the earlier slide, that ox- oxaziridine. So in this case, oxygen electrophilic oxygen is the source of electrophilic oxygen is the oxaziridine reagent. But here its stereochemistry is driven by the this entire functional group. This functional group is used as a chiral to drive the chirality in the molecule. So this is the product in this case, and minor product also we get, but the minor product is comes from the uh, the minor product in this case will be the hydroxy group, which is alpha. This will be definitely the minor product among these two. And the diastereometric ratio also mentioned here. So diastereometric ratio is 94 as to 6. So that's the diastereomeric ratio in this case. And if you use the same reagent on the starting uh, uh, in this fashion, so let's say this is the starting. So this is the starting which has the directing group, which is the alpha directing, right, which is directing downward. So at that time, same LiHMDS abstract the proton, and in this case, then oxygen, electrophilic oxygen we get from the oxygen. So the hydroxy group will be the beta in the same. So if you want to get selectively the alpha or beta, then we can use the chiral auxiliary. So in this case, the chiral auxiliary that use. So if you have this type of starting, and from this we want to get the this one, or else we want to get the selectively. beta hydroxy, let's say here acid, then we can do that one by using this type of approach. So what we can do, we can do use the chiral auxiliary. So we can this acid we can couple with the chiral auxiliary. In this case, the chiral auxiliary was this entire group was the chiral auxiliary, right? So this in presence of the coupling reagent, let's say DCC or any carbonic acid coupling reagent, we can couple this entire chiral auxiliary to. So the chiral auxiliary is this one, right? So if you use the beta, and here in this case, what are the other groups here? pH. Mhm. So this is the, and here there is N H. So if we couple do the perform the reaction, we get the BN, then the structure is nitrogen with the attached chiral auxiliary, and right. So we get this chiral auxiliary, and when we use the star reagent, which is reagent of the LiHMDS and the oxazidine, uh, we get this product. And similarly, when we want to the in this case we get the beta alcohol hydroxy group, right? And similarly, when we want to the alpha hydroxy, so we can use instead of this chiral auxiliary, we can use another chiral auxiliary. Let's say in this case we can use the nitrogen double bond O. So this chiral auxiliary we can use this chiral auxiliary convert into attached to the this hydroxy group. So as mentioned, this type of kind of intermediate, and which is then created with the LiHMDS and oxazidine, it gives the alpha directing hydroxy group. So here we can use the take the advantage of chiral auxiliary as well as the uh, this oxazidine electrophilic oxygen donating reagent to get the selective either alpha directing or the beta directing hydroxy acids. So so in this case, two concept is important to note. So the first one is the use of chiral auxiliary, and second is the use of oxazidine. In this oxazidine gives us the cationic oxygen, and this chiral auxiliary drives the selectivity, stereo selectivity. So these are such concepts that you need to keep in mind while if you want to do the any kind of synthesis in lab, or also in the paper if you want to uh, do the total synthesis or synthesis, then this kind of approach you need to use. So I have mentioned the detailed mechanism in the few slide for the this Barton that I will not discuss here. So the another reaction that we are looking for the oscillation reaction. So this reaction is not covered by the professor. So I have just purposefully kept mentioned here because this is also one of the important reaction, which is a NAP reaction, and it involves the conversion of nitro to the keto functional group. So if you have the nitro substrate, and let's say the this nitro is converted into the keto, and the reagent is for this one. We need a starting material with the nitro group, and the reagent is very simple, which is the NaOH and H2SO4. The first step is the NaOH, and second step is the H2SO4. And if you look at the detailed mechanism of this one, so what happens in the first step, we have the such starting which has the proton, right? So the proton get abstracted by the hydroxy group because this alpha proton is obviously the acidic, which is adjacent to the nitro. This acidic proton get abstracted by the hydroxy group, the dehydrolysis occurs, and we got the intermediate, which is nitronate intermediate. This on this nitronate intermediate, the first step was the base one, right? Now, once we got this intermediate, we do the reaction with the acids. So this will convert into the nitromic acid because we are using the H plus, right? So this get convert into nitronate, convert into nitromic acid. And once this nitromic acid is formed, in terms of acids, what happens? The dehydrolysis occurs, and we get the uh, this is the NO bond formation. On hydrolysis, it NO convert into uh, the imine bond, which is here. The water gets attacked on the carbon of this imine bond, right? C double bond N. So the hydrolysis groups occur at this attach at this stage, which is further uh, on this hydrogen gives the HNO and the keto as a product. So in this case, overall the reaction we get the uh, release of the NO2, N2O, sorry, and the water get removed, and we get the keto in this case. So the conversion of the primary or secondary nitroalkanes to the corresponding carbonyl compound is the NAP reaction, and the reagent was very simple, NaOH as well as H2O support. That condition is we need to have the nitro compound. So if you look at the synthetic utility of these kind of reactions, so let's say here we have the nitro starting, and this converted into the with of this uh, NaOH in ethanol at 0 degrees Celsius. If you look at the reaction condition, very mild reaction. So at 0 degrees Celsius, it convert, and the second reagent was 3 mole HCl, which is also very dilute HCl, right? And also 0 degrees Celsius for the 12 hours, it gives 68% of this oxidized product. This another question, another also the example, which is nitro convert into the uh, nitro convert into the keto. So here the reaction condition is slightly different. Not necessarily you need to use H2SO4, you can use here HCl also. Further, ice cold KMO4 also do the same job. This first reaction do the same job for this. And this is a similar kind of NAP reaction. It's not exactly the NAP reaction, but it's similar NAP reaction. Further, you can see here, we have the nitro here and also TBS protecting group. So at that case, what happens? So the disulfide linkage, this is the reagent, and to equivalent of PME3 in PHF, it gives the imine bond formation, and which on hydrolysis, obviously we have seen imine convert into the uh, its corresponding keto carbonyl group just by doing the hydrolysis, which is just in workup condition also it can convert into the imine to keto. So this is the NAP reaction, which has like quite good synthetic utility in the synthesis of some of the natural products. Further, we are seeing the use of LDA, LiHMDS. These are the some of the bases. This again and again some questions came. You have seen already in the assignments. Also, you generally see in the any competitive examination, and also just in day-to-day lab at the chemist. So the this kind of base is generally used. The purpose of this using the base is a bulkier base. It isn't a non-nucleophilic. You generally abstract the protons only. So if you have the one of the example, let's say this I have purposefully kept here for the comparison, and this is A and B two examples. But in this case, we are using the we change the sequence of the reagent addition. So if you look at here, why the addition sequence is also important. In this case, if you look at the reaction sequence, we have used the LDA. Obviously, the LDA abstracts the proton, it gives the anion here, right? That we already know. Once this anion is formed, we use the pH, SC, pH, so that the diselenium, right? So it has the electrophilic SC pH we get from this one, so it's delta negative and this is the delta positive, right? So once this enolate form, the negatively charged attacks on the SC, and this SC, pH, SC minus and pH, that entire group get leaves. So we get the formation of, in the first step there it was the SCPH bond for C SCPH addition. So the first step was, I will directly mention here. So the first step here is the SCPH formation, right? And another step is like again we add the LDA. So if you add the one equivalent of this one equivalent, let's say it is also one equivalent, one equivalent, right? One, and this also the one equivalent apps. If you add the one equivalent, it will abstract the proton, and also addition of occurs only one. And then we add the again in the next step the LDA and the methyl iodide. At that time, what happens? The remaining protons. So the initially there is also one another proton remaining, right? So the remaining proton get attached to the. So if you look at the stereochemistry of these intermediates, so the if I draw the entire structure here, so the stereochemistry of this intermediate looks like. So the SCPH will be on the dotted side, and this hydrogen is on the beta side, right? The next step will be converted into the this one LDA plus methyl iodide. So if you look at this one, this is the hydrogen is the exo, and the entire structure will be inside, right? So the ACPH is also will be in the first step will be remain exo, but when you abstract the proton, it get into the planarity, right? Because the double bond enolate chemistry that we already seen, the enolate when we abstract the proton from this one, so when we abstract the proton, the next step will be it forms the enolate which has the O negative. So once we abstract the proton, so once we abstract the proton, so this group converted into the plane. So now the stereochemistry of this one will be the in the plane, right? And once when this goes down to this one, the addition of this methyl group also takes place again on the exo side. So what happens when the addition takes place on the exo side? So the this ACPH comes again now comes now in the same plane with the sorry above the plane to the methyl because these hydrogens are exo hydrogens. So the whichever incoming group which is newly added on such systems, so that will be comes on the exo side. So that's why if you do the sequence like LDA plus PHACPH followed by the again LDA and methyl, the SCPH will be on the above side. But let's say if we want a different product among this one, so what we can do, so if you want the SCPH on the same plane with the hydrogen, then we need to change the addition sequence. So we first need to add the LDA plus methyl iodide. So it gives the methyl iodide in the first step will be in the first step that methyl iodide will be on the exo, right? So if I just draw the structure of the previous one, in that case, initially it was like this, right? So this is for this, right? Initially it was like this, right? So first step, then this is the second step, enolate formation, and this is again the addition of new incoming group. So it will be the methyl iodide. This is the product in this case that's the this product number 25, right? And in the second, if you look at the if you know on this methyl on the plane with the hydrogen, sorry, the ACPH in the plane with the hydrogen, then we need to change the reaction sequence. In this case, we have the LDA plus methyl iodide first, followed by LDA plus SCPH. At that time, this SCPH will be on the plane which is same with the hydrogen. And if you look at again the next reactions, so in this case, up to here it's okay, right? Now, if you are if you perform the same reaction condition and these two different type of intermediate, so I will just to take this slide. If you want to perform this entire reaction on this uh, Right. Now we have already seen up to here it is okay, right? Now if we perform the same reaction, that is H2O2 plus 0 degree Celsius on these two, so what happens? We get the two different products. And why this is two different products? Like we get the this is the elimination reaction, right? Because we have already seen the this SEPH get oxidized and followed by the elimination reaction. And also the condition is for the elimination, this oxidized SEPH, SeO, this and the hydrogen should be on the same side. So in this case, what happens? So this SeO bond form gets formed, right? So this SePH and this SePH is in the same plane. That's why the olefination occurs at this like this method, and also the oxidation, sorry, the olefination here, because according to the uh, Set-Zipf's rule, which is like olefin should be the highly saturated olefin is the more stable, right? So this is the quaternary olefin. So that's why the oxidation occur in this one. And uh, in this one also you can see the SEPH and the hydrogen which is not in the same plane. That's why the it will look for the another hydrogen. So the another hydrogen is come from this methyl group, and this methyl group is like obviously which has the alpha hydrogen. So the hydrogen get abstracted and followed by the elimination and olefin formation which occurs. We get the product to two different products, and these two different products because of the stereochemistry difference between two this. So so this addition sequence difference makes the uh, gives us the two different products. That's the reason the stereochemistry and this stuff is very important in the day-to-day life of the chemist. So these were the some of the questions, some of the problems that I have taken from the course, and hope you will enjoy this problem. There are also some problems that I have kept here and that we can discuss, uh, especially let's say this slide, and this is also the similar kind of reaction that and also the set of reaction that already we have seen. This is the SOCl2. We call it SOCl2, right? S double bond O, Cl and Cl. We have seen the reaction of such reagent in the Swern oxidation. So when we have the hydroxy group, what happens? These hydroxy groups get from the O, right? So this kind of intermediate get formed and the Cl get removed. So in this case also, when the SOCl2 react with this alcohol, what happens? The hydroxy react with the SOCl2. So the entire set of structure, entire structure will remain same. So this is, I will keep the R as it is. This dotted O, and this will be the S double bond O Cl, right? So this is getting formed in the first step. And now if you look at the stereochemistry of the SEPH, which is anti. So what happens? This neighboring group participation, NGP, we call it as NGP, that occurs in this case. And this lone pairs or electron pairs on the Se, selenium attack on the carbon, and this entire group now this entire group is now a very good leaving group. So that's why this lone pair on the Se attacks on the carbon, which has the oxygen and this entire group. So it forms an intermediate 29. This intermediate gets formed in this reaction, and further reaction with the triethylamine and although triethylamine and this chloroform is in the DCM, so it gives the elimination, and in the elimination, the stereochemistry. If you look at the stereochemistry will be retained, right? So this one and the hydrogen which remain on the syn side. In this case, it is on the Z side, right? And this one and this is the on the opposite side to each other. So we get the olefin here. So this is the one of the uh, classical example of the neighboring group participation, and this drives the stereochemistry in the following form alkene. So you can refer this as one of the example for the neighboring group participants. Also the set of reagents that I have mentioned here, which we have already seen the use of the SOCl2, reaction of the SOCl2 with the alcohol, occurs, and also the SCPH selenium-based reagent. So this was the some of the slides that I have taken from the course. So we'll stop here for today. So I have mentioned kept some remaining slide that we have not discussed, but you can refer that from the OneDrive. So which involve the more example of this uh, Fleming-Kumar oxidation, and also some problem based on the enolate chemistry that I have also added on the slide at the end of the this slide that I will add. So you can refer that one. So we'll stop here for today. So thank you for joining.